Basically, the research is about these worms, which are called waxworms. They are larvae of lepidoptera called Galleria melonella. And the habitat of these worms, of this animal, is the beehive. So they live and thrive and eat, do everything, their life cycle within the honeycombs of a beehive. And that's why beekeepers usually consider them as plagues, but they can kill it all, a beehive. So I had my beehives and I found these worms in there, put them in a plastic bag, and I found the plastic bag riddled with holes after a few hours. So I went and checked the plastic in there and I found it was chemically modified. That's when the whole story started.
Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers, because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD and working on a product to help people overcome these problems, because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
Go above and beyond.
they become very good at what they do, but only
0.1%.
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
With Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius podcast, now part of the Finding Genius Foundation. I have Federica Bertocchini. She's in the Department of Microbial and Plant Biotechnology at the Centro de Investigaciones, Biológicas-Margarita, Salas in Madrid, Spain. And we're going to talk about two enzymes, that can destroy polyethylene in a few hours and biodegrade it. So, Federica, thank you for coming.
Thank you for inviting me here.
Well, if you would tell me first about your background, how did you get involved in the degradations of plastics? And then I want to ask you about your current work.
Sure, yes. So I'm, by training, I'm a molecular biologist, and I've been working using molecular biologist tools in the subject of developmental biology, studying embryos of vertebrates. Particularly, I was studying chicken and reptiles as experimental systems. So basically, you study how an embryo develops, how cells arrange and choose, so to speak, their fate. But then I had always carried with me some environmental concern and interest. And as a side project several years ago, I started looking to the environment for little invertebrates, small animals that could degrade plastic bags, which are made out of polyethylene. And that's where the whole story started.
Why were you looking for, and how did you even know that you could find creatures that would degrade polyethylene bags?
No, I didn't know. I was very naive, actually. In fact, in the field is, let's say, dominated by, well, more than dominated, it was initiated by microbiologists, because naturally people look for microorganisms like bacteria or fungi, but I didn't have that bias because I was coming from another field. In my head, I was thinking of more like small animals in the environment, and I happened to find one by chance. I was looking for something of the sort, but I found my waxworm, let's say this waxworm by serendipity, by chance, being a beekeeper. So these are animals that plague beehives.
What do you mean? So what animals that are around beehives, that plague beehives? What, bacteria, the enzymes, or what are these?
The worms. So basically, the research is about these worms, which are called waxworms. They are larvae of lepidoptera called Galleria melonella. And the habitat of these worms, of this animal, is the beehive. So they live and thrive and eat, do everything, their life cycle within the honeycombs of a beehive. And that's why beekeepers usually consider them as plagues, because they can kill it all, a beehive. So I had my beehives and I found these worms in there, put them in a plastic bag, and I found a plastic bag riddled with holes after a few hours. So I went and checked the plastic in there, and I found it was chemically modified. That's when the whole story started.
And so the worms they didn't just chew. Was it the worm's saliva, or were there certain chemicals in it that you could see the plastic was actually degraded?
So at that time, we didn't know how it managed to do that. We using some chemical tools. We found the plastic was chemically modified. Probably there was also some chewing, but beyond that, we found oxidation of the polymer. And also, when this worm, they make a cocoon and they transform in moth, except like when the caterpillar transforms in a butterfly, it's just the same thing. And the way when they make the wee cocoon, they freshly make cocoon in contact with the plastic bag, it produced some debris of plastic. So there was something coming out of the mouth that was producing this effect. That's when we started looking to the saliva, found out that in fact the worm can oxidate and degrade the plastic bag via its saliva.
Okay, so then did you try to isolate the chemicals inside the worm that does this?
Yes, then we went to see what's in the saliva. We were looking for, the first thing we were looking for were basically enzymes. Actually, the first thing we did was take a look at the saliva, and there are some tools that allow us to do that, like an electron microscopy, so you can see the saliva at very high magnification. And we found it full of proteins. Enzymes are proteins. So at that point, we start try to identify among these lots of protein in there, which one potential candidates. And again, we apply some biochemistry there to reduce our pool of candidates until we found these two enzymes capable of reproducing the effect of the saliva, meaning degrading polyethylene.
So these enzymes are just a normal part of their saliva? Like, have you compared the worms eating regular worm food to plastic? Is the saliva the same or different?
The saliva, we didn't do that, but I don't think the worm eat the plastics. Plastic is not food for the worm. The plastic, the chemical composition of plastic is too poor to be able to sustain the growth and the survival of the worms. And also we did the kind of experiments. The worms are not good in a diet only of polyethylene.
The people eat candy sometimes, and that's not good for them. They eat mostly other stuff. Maybe the worm just eats it and moves on, looks for more food.
We are not the only lab working on this. And when you look at the feces of the worm that has been exposed only to plastics, some plastic is munched, it's broken, it's partially degraded, but then it's lots of feces as well, so it's expelled. So plastic is too poor. A diet only with plastic will cause the worms at some point to stop its life cycle. We did that, so we can say that.
So was the worm just breaking through the plastic and degrading it, like punching through it to get out?
Both things, probably punching through it and degrading, because you have this capability of breaking down using the saliva, using these substances in the saliva. So it's not only a mechanical effect. This is important. It's a chemical effect. There is this capacity.
Right. Are there other substances where the worm has the same behavior? Like, what if you put them in a paper bag? Would they chew their way out the same, or other kinds of maybe other kinds of plastics too?
Well, they make only polyethylene. Other people found out that the same worm can break down polystyrene. And then if there are others, so we are trying others, so we don't know yet. So
what your goal now is have you isolated the enzymes in the worm's saliva that do the breakdown? Have you figured out the mechanism of action?
Yeah, that's a key question. So we found out which enzymes were the culprit. So, okay. And then what we didn't isolate them from the saliva. We made them in the lab. There are companies that can do that. You can do also in the lab, like we could do that, but these are relatively new proteins, new compounds, so it's not immediate. So it needs some work. But the good point is that I bought this enzyme from a company, a plant company that do that. And they managed to reproduce it in the lab. So they're called recombinant proteins. So we don't have to store and to have billions of worms to retrieve saliva. We just can produce the protein in the lab. So this is the first point. This is important. Now we need to reproduce on large scale, and we are not there yet. But the proof of concept is there. Now, how the enzymes work? This is a good question. We don't know. Chemically, how they work, we have no idea. We are trying to figure that out right now as we speak.
How do you intend to apply it once you figure this out? How do you think it could be scaled up commercially?
Well, we hope we can. So clearly, nowadays, to talk about degrading tons of plastic, this is a bit utopian. But the idea is to use these enzymes. These enzymes represent a low temperature solution in a water solution, so you don't need the specific arrangement. And the plastic, it doesn't need to be pre-treated. So it's relatively easy. So we can imagine a controlled place like container or something, put the plastic there and pour a solution with enzymes in there. So this is how it could be done. So again, thinking in terms of tons and tons, now we cannot do that. It would be highly unrealistic. But maybe we can think if we manage to produce lots of these enzymes at low cost at some point during this path in research, we start thinking of contributing a percentage of plastic waste management with reduction.
So what are how many stages are there in the breakdown process? Like, have you identified chemically the intermediate compounds formed and the final ones and how this works?
Oh, that's a good point. So usually we found some degradation products, which are what you expect when you oxidate a molecule like polyethylene. I mean, this is what chemists describe. So take the polymer, you break it in small pieces, and you attach oxygen in different forms, in different shapes. So you have something which are called ketones, some other compound which are called acids, etc. So this is exactly what you expect from degradation. Can we degrade more than this? Well, we don't know that. Can we degrade completely to CO2? Do we want that? Maybe not. Maybe we could use this small oxidized compound to do something else. Maybe that could be useful to the chemical industry.
Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now back to the show.
Okay, but again, so do you have a chemist on board that can figure out, again, all the reactants, all the products, manipulate the reaction to make it faster, to reduce the, to have more products?
In these 2 sentences, you summarize years of research, which are good. Again, you pointed the finger in the key issues. So we had the chemist in the lab, and the chemist, and then we used also facilities outside, because the type of chemistry we need to try to understand this is a different kind, a different types. We are collaborating. So this is really a multidisciplinary effort, even talking only about chemistry. And then this for what is produced, but then even in terms of the enzymes, how to optimize them. So we are working on the structure. The structure meaning to see how the protein is arranged in the space and see how it could degrade plastics. And that's a key starting point to be able to improve its production, its stability, and eventually its function. So there are all little steps that we need to take, and we need different competencies on board. And we have some of those, with some we collaborate.
Okay, so these worms can break down polystyrene, polyethylene, etc. Commercially, are you focusing on polyethylene because there's a whole world of information just for that plastic, or are you going to try to figure out the mechanism for multiple plastics? Like, what's your goal?
Yes, the old thing you said. So we are focusing on polyethylene. Was the first I started working on, plastic bags, and then it happened to be that the more produced, 30%. But clearly what we are after are the polyolefins. So I would say, for example, if you consider polyethylene, polystyrene, and polypropylene, I think we go around 70% of plastic production. That's a lot. So that's the target. Probably future will be mixed plastic. If you might be able with the enzymatic preparation to avoid the step of separation of plastic when we manage the plastic residues, there will be a very good step.
Okay. Again, have you found any intermediate products that are useful? I mean, what if
the intermediate? Yes.
What if you could have the worms break down the plastic back into monomers or useful components where you could recycle it? What is the goal? Is it for the worms to just degrade this totally to some other substance, or to partially do it so that they can be recaptured maybe?
You can do several things. So the worms, to go to the monomer, I don't know that. I don't know if chemically that is possible. But, for example, we found small oxidized compounds. Some are ketones, some is an acid called sebacic acid, which are useful in the industry. There's all industry that try to produce, for example, the ketones, because they might be used for example, as solvents or other compounds. So if there are compounds that the industry can use, alternatively, what could you do? For example, you could try to engineer some bacteria and see if you can, for example, completely degrade this compound or transform whatever is formed in some other useful compounds for the industry. Now, the transformation to monomer, I'm not sure. I don't know if that would be my target right now. Chemically, that would be a difficult step for the time being, as far as we know. And then if at some point we realize that we can do that, maybe we can also get into that. But so far, I cannot say anything like this because we are not sure about the chemistry of that.
Okay. Well, again, so how long will it take you to figure out what the chemistry is, or which part of it?
It depends on the money. It depends on the funding. If I get 5 million today, we might do it pretty fast. If we go on like this as I am now, it's going to take forever. This is always the key question, because the funding is critical. You need biochemists, you need chemists with different expertise, you need lots of things, and the fund into the proper experiments. So this is always the bottleneck for us.
Yeah. Have you been able to identify any of the components yet, or not yet?
Yeah,
Like when
I told you.
at the
No, sorry, what components?
Oh, again, the digestion of it. What is it digesting?
Yeah. But not digestion, though. Sorry, not digestion, just breaking down, because digestion implies, breaking down. There's more oxidized molecules, as I said, ketones, some acids, which could be used by the industry. These we identified. We identified in a proof of principle experiment, so very small amount of enzyme and very small amount of plastics. And I'm sure we could do more in that direction if we had more enzymes and more plastic. But already it's a good start, because we found some compounds it could be reused, and it's what is expected actually. So it's pretty good.
Right, but of the compounds you've already found, are any of them surprising to you? Can you describe any of them?
They're called ketones, and one typology. Another is a basic acid, which are not surprising. Exactly what you might expect. If from a degradation or polyethylene, you find something like this, it's okay. Okay, it's not surprising. It's pretty good actually. Ketones and sebacic acid. These are the major compounds we found.
What is that?
Again,
What is ketones? What's that special?
There's ketone is a specific group, chemical group, which is oxygen, one part of the molecule, and the sebacic acid, again, oxygen in different shape. And these are called small oxidized molecules. This coming from the polymer. The polymer has been chopped in pieces, and you have oxygen attached. But I want to point out, which is just we found this working with a very small amount, and we might increase both the quantity and the quality if we use more. If we work with more quality, more amounts, both of plastic and enzymes.
Well, what's interesting chemically about the compounds you're seeing so far? You said that these are rare compounds. Have they ever been seen before?
This is what you expect from and this is exactly what you expect from the oxidation of polyethylene. So it's not surprising. They're interesting because because the polymer is broken down. Second, because you could reuse it. The chemical, these are compounds that are used in the industry. So chemical industry, different kinds of sort.
So you can recover a lot of the material.
Yeah, it can recover. Yes, you can recover.
So instead of monomers, which may be ideal, maybe not, but you could still create useful, recoverable products. That's
absolutely cool. This is the part. What I mean, I mean to say the proof of concept worked pretty well. Proof of concept. So we need more enzymes. We need to scale it up and see what else we can find, and the quantity, because we don't know the quantity, the quantification of enzymatic reaction. There are all little steps that we need to work out.
Can someone just with chemical formulas calculate the theoretical production limit of the chemicals?
Not yet, because for the quantification we need to do a different kind of experiments, but we need the limiting factor are the amount of enzymes. So the first step we need to do is to produce more, and so that's what we are working. We are trying to
the price of the degradation products in the market. What if you figured out how much those products were worth if they were, they need to be purified, of course, but let's say it's, $1 a pound. And you get three products.
No, I cannot do that. I cannot.
Look at the mass of it and see if how worth it this process might be.
I see your point, but not really. I didn't do that because I see the importance of this point for the industry. And if the industry wants at some point to invest in that. So the industry is not investing in that. But second, and I'm stressing this point, this is just the beginning. Because I don't want to limit. We found this, they have these 3 compounds, how much is worth? No, we have these 3 compounds to start with. And I'm sure we can find more. Because again, we have a limiting solution and techniques we apply. So I don't want to fix my attention on this, because it will be dangerous, because maybe I don't see the whole scenario. I don't want to lose sight of the whole scenario. This is just the beginning of the story. So I haven't done this calculation, because for me, it's not the moment to do this calculation. It's not, we might really lose something there if I stop at this step.
So what are your next steps now in the experimentation?
On one side, they try different plastics. On the other side, producing the proteins. This is key. Third side, also, we are already doing that. We are quite ahead on that, characterizing the structure. The structure of the protein is important for optimization. They're all going. These three things are going the same direction.
Okay. What are some of the plastics that, if they could be broken down, people would be amazed? Are there any particular plastics that are really difficult to do?
This one is the polyethylene. Polyethylene, the polyolefins, polyethylene, polystyrene, polypropylene, and PVC. These are the most difficult, the most resilient, the sturdiest. And these are different from the PET, which is the plastic bottle, for example. Those are the plastic bottle is less resilient. It's a polyester. But the other one, polyethylene, this is the aim. This is where the interest is. In a way, where the interest is, although the industry is kind of absent there in terms of investment for some reason.
What about in nature? Is anyone going and sampling, let's say, PVC that's been laying in the dirt for years to see if there's any degradation, or other plastics in the environment to see if there's other natural creatures or bacteria that do degrade these substances?
Absolutely. This is where the field, this is how the field of biodegradation of plastic started. And we were talking about it a few decades ago, and that's what they do constantly. They, meaning the people in the field. I entered the field just a few years ago. And with they, I also refer to the microbiologists. So they went into landfill sites and check out piece of plastic, this polyolefin, and look for bacteria. But so far, the search for bacteria or the quest for bacteria didn't give much results. Bacteria have some troubles to attach and degrade such a sturdy material. For the time being, maybe at some point we found something. For the time being, it's still problematic. Insect came into the picture a few years ago, and now we found these two enzymes, which are, for the time being, they are unique. Maybe, again, hopefully, some more will be discovered. But for the time being, these are the first one capable of degrading PE.
Okay. Well, very good. Federica, where can people find out more information about your work and keep tabs on it?
I have a couple of websites. One is I formed set up a spin-off called Plastic Entropy. And there is a website, and I have all my personal and my information are there. I also have a LinkedIn page, all these social media. I don't have Instagram though. Maybe it's a problem. Except for that, websites, LinkedIn, and that's where my information are.
Okay, very good. Well, Federica, keep working. It's a very interesting field. So, thank you for coming on.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.